An Olympic track runner started from rest and had an acceleration of 1.9 meters per second squared for 4 seconds. Then had 0 acceleration for 9 more seconds of a race. The runner's finishing time for the race was 13 total seconds. Can we find the runner's instantaneous speed at time t equals 4 seconds? So acceleration is the change in velocity with time, and it's actually the derivative of the velocity versus time graph. So just to get a handle on what's happening in this problem, I'll just sketch for myself some axes. The graphs that are really important here are velocity versus time and acceleration versus time. Now, they said that the acceleration was 1.9 meters per second squared, and that lasted for 4 seconds. This implies what is called constant acceleration, meaning the acceleration isn't changing. When anything's constant, then it should have a horizontal graph. Okay, so let's let that be the acceleration for the first 4 seconds. Then apparently the acceleration jumps down to 0, and it holds that 0 acceleration for the rest of the time. And here at the end is the 13 seconds. Okay, so since acceleration is the derivative of velocity, and velocity is the antiderivative of the acceleration, we want to be able to graph the velocity function. We need a little bit more information though. Where do we start our velocity graph? They said the runner started from rest. Now rest implies that the velocity was 0 at the beginning of the race. Now over time, the velocity increased in a nice straight line that's slanted until it reached a maximum value. And here, because there's a sudden change in the derivative, there's going to be a sudden change in the slope of the velocity. So what does the velocity do? Well, there's 0 acceleration. That means the velocity does not change from there on. And so it can be really helpful to be able to draw these graphs in order to inform how we'll solve the problems. So now that I have that basic graph drawn of the situation, we want to find out what the speed was at 4 seconds. All right, so an integration could definitely help us do this. We'll want to find the change in velocity. And that comes from integrating the acceleration function. This is the general formula for it. All right, so let's plug in our numbers. We'll get 1.9 t integrated from 0 to 4. 1.9 meters per second squared times 4 seconds. It's 7.6 meters per second. So that's going to be the speed that the runner attains. Starts off with 0 speed, after 4 seconds has increased to 7.6 meters per second. Now we could have solved that using the algebra formula as well. The formula is delta V equals A delta T, or AT, where T is the elapsed time. But that formula is derived through calculus for constant acceleration. And it would only work if you had constant acceleration or if you knew the average acceleration. And that is the subject of a future video. Now let's figure out how far the runner had traveled in 4 seconds. Okay, so for that, since it asks about distance, we'd like to create one more graph. Let's create a graph of the position versus time. Now, when the velocity is linear and slanted like that, it's going to create a parabola in the position versus time graph. Because there's acceleration, there should be a curved position versus time graph. Now, once we get to this important point where things change, that's when our position versus time graph is going to straighten out. And it's going to become just a straight slanted line. We're asked to find how far the runner had traveled in 4 seconds. So we're asked to find x of 4. Now, in order to do that, we're going to use x from t equals 0 to 4 equals the integral of the velocity function from 0 to 4. So we need a formula for this v versus t graph. Well, luckily we have enough information to find the formula for this segment of it at least. All right, so it's sloped up for a while. There's a run of 4 seconds and a rise of 7.6 meters per second. We need to know what that slope is. Okay. And the slope is simply the acceleration. So it's going to be 7.6 over 4 seconds. Not surprisingly, I think, the slope is 1.9 meters per second squared. So what formula does it have? V of t equals a t plus vi. And since vi is 0, it's just 1.9 t. Okay, so we need to find the displacement of the runner from time 0 to 4 seconds. We'll integrate the velocity function. But what is the velocity function? I wrote it over here. So let's plug this in. All right, so the formula that we get will be 1.9 t dt. We want to find the antiderivative. Okay, now we just want to plug in the 4. And let's see how far the person had ran. Fifteen point 15.2 meters. All right. Lastly, we're asked to find the runner's speed at the end of the race at t equals 13 seconds. Well, that question is more of a concept question than anything. If you look at the velocity graph, you can probably answer it. They're asking us, what is the velocity at 13 seconds, right? Well, it's the same as it was at 4 seconds. 7.6 meters per second. It hinges on the fact that the acceleration is defined piecewise. There's a change in it. And so we have to be aware of that when we go to solve the problem. And both the graphs and the calculus can help us understand the problem. We want it to all tell the same story. So the velocity at 13 seconds is 7.6 meters per second.